In this video, I want to talk about K versus Q in the form of KSP. Now, when we're working with K versus Q, most of the time you're given a K value and you solve for Q. Remember, the difference between K and Q is that Q is given initial concentrations or pressures if you're dealing with Kp, and K is dealing with equilibrium values. So once I figure out my Q value, I then compare it to K. Now, this is the exact same thing as what we've done before, except it has a little bit of an extra meaning, okay? If I am solving for my Q, and my Q just so happens to be less than K. So let's say, again, K is 50 and Q is equal to 10. What that means is that my reaction will have to shift to the products in order to reach equilibrium. And if I'm shifting to the products, think about the reaction that I'm dealing with now. I have a solid breaking apart into little aqueous ions. So if I have to shift to the product side, then that means that I am able to make more of these ions. If I can make more of these ions, we call that an unsaturated solution. So if Q is less than K, my reaction will shift to the products, meaning that it is unsaturated. What that term means is that I can dissolve more of that solid in there. Unsaturated, I can dissolve more solid and to make more ions. If I solve for Q, and let's say that it is greater than K. So again, let's just say K is 50 and my Q value is 60. What that is going to do is cause my reaction to shift to my reactant side. Now, if we think about it here, if I have to shift to the reactant side, then that means I'm no longer dissolving into my ions. I've now stayed as a solid. If that's the case, then we call that supersaturated. So supersaturated means Q is greater than K, so therefore I can no longer dissolve my ions. I can no longer dissolve any more of that solid, so it's going to stay as a solid. This is where a precipitate forms. So a precipitate forms when the solution is supersaturated. Now, if I solve for Q and I find that Q is exactly equal to K, that's the number 2 right here, then that means I'm at equilibrium and we call that a saturated solution. So these terms are very important to put in with my explanations and justifications when I'm working with K versus Q. Now, when do they ask this question? What's applied? Anytime they ask a question, they will say, will a precipitate form? Okay, so the main question that they're asking with K versus Q for KSP is, will a precipitate form? And the only time when a precipitate forms is if Q is greater than K. So let's do this exercise together so we can get a sense of how they will ask it on a free response type question. So what I have given here is a value of CeNO3 and KiO3. Well, when I mix these two, the solid that's going to form from that is CeIO3. So let's write that down. So CeIO3. CeIO3. And we'll have a 3 out there. This is the solid. Now, if that solid dissolves, if it's soluble, then it's going to form Ce3 plus ions plus IO3 minus, and to balance that, we need a 3 here. So this is just writing my reaction based upon this. This nitrate and this potassium, they are not present in here because they will be spectator ions in this process. So here's a kicker here, all right? you would think probably that you plug in that molarity for an initial concentration and this molarity for its initial concentration, but that is wrong. Here's the reason why. If you worked the equilibrium lab with me, we talked about if I mix two things together, if I'm adding two solutions together, or if I'm mixing two solutions, what that is going to do is change my molarity. The reason why it's changing my molarity is because when I add these two things together, I'm changing my volume. And a volume change changes molarity because molarity is equal to moles over liters. So in order to figure out this initial value as well as this initial value, I'm going to have to use the very famous dilution equation. So I'm going to use the dilution equation to solve for this new molarity. And I'm also going to use the dilution equation to solve for this molarity. So we did this when we worked with the equilibrium lab if you were here in my double period class. If you're in my single period class, I'm sorry, we didn't do the lab. Here's how I did it, okay? So here's what I'm going to do. For Ce3+, I'm going to take its first molarity. So here's the dilution equation, by the way. M1V1 equals M2V2. M1 is this molarity. V1 is the volume that you started with. M2 is the molarity that we're solving for our initial value. And V2 is going to be the volume once we put these two volumes together. So these two volumes together added up is going to be 1,050 milliliters. And if we want to convert that to liters, we would divide it by 1,000. It is okay if you're working with both of those volumes in milliliters to leave them because their units will cross out. Now, where we're getting this equation from is molarity times volume is equal to moles. So we're basically saying, hey, we're not changing the moles, we're just adding more volume, right? So the moles initially is equal to the moles at the very end. That's why we're setting this equation equal to one another. So here we go. Let's plug in that stuff. So we get 4 times 10 to the negative 3 times this volume, 750, is equal to the new molarity times the new volume, which is 1050. I solved for the new molarity, and I ended up getting 0.00286. So 0.00286 molar. So this is the molarity that I'm going to plug in right here. So 0.00286. Now I'm going to do the same exact thing with the IO3. So M1 V1 equals M2 V2. M1 is the initial molarity, so 2 times 10 to the negative 2. V1 is the initial volume, which was 300. M2 is the new molarity I'm solving for the initial value of that. And V2 is the volume added together once I mix them, so 1050. Now this will help you out in acid-base as well. Whenever I mix two solutions, you always have to find new molarities, okay? And you find the new molarities by M1V1 equals M2V2. So if I solve for M2 for the IO3 minus, I end up getting 0.0057. 0.0057. So that's the value for this concentration, which I'm going to plug into here. Now the whole point of this question is asking, will a precipitate form or not? So if I'm trying to figure out if a precipitate will form or not, I'm going to solve for Q. And remember, Q uses those initial values, so that's what I'm finding right here. I plug it into my Q expression, which is the exact same way I would write an equilibrium expression. So IO3 minus to the third. Now I plug in those values. So this value goes in here. This value goes in here. And don't forget to cube this value. So when I solve for Q, I end up getting 5.3 times 10 to the negative 10. Now, that's a 5.3 right there. Now that I have solved for Q, I get to compare it to K. So my K value is given. It's 1.9 times 10 to the negative 10. So I'm going to write it up here. K is 1.9 times 10 to the negative 10. And my Q value is 5.3 times 10 to the negative 10. Because they're the same exponent, I look at these numbers to see which one's greater. So 5.3 is greater than 1.9. So Q is greater than K. Now, this gets us to familiar territory. If Q is greater than K, what that means is the reaction will shift to the reactant side. And if the reaction shifts to the reactant side, that means that it is supersaturated, meaning that a precipitate will form. And so that's how you work the Q versus K for these KSP expressions. The approach, the method has not changed. It's just a little bit extra. So I have to find new molarities before I plug them in as my initial values. And secondly, once I find that Q is greater than K or Q is less than K, it has a specific term that I give it, and it's answering whether or not a precipitate will form. So in this scenario, yes, a precipitate will form because since Q is greater than K, my reaction will shift to the reactant side, meaning that you have a supersaturated solution. So I hope this helps you be able to work your Q versus K problems. They like to ask this every now and then on free response, and you will always know to use this approach if they ask if a precipitate will form or not.